Well, hello and welcome to the stream, everybody who is still watching. Thank you, Heather and Lars, for the introduction. I really appreciate it, and I hope you all learn a little about machine learning, because that's what I'm here to talk about. So happy Tuesday or Wednesday, I guess, depending on where you are in the world. My name is Nick Larsen, and I love artificial intelligence. I'm here to give you a talk today that is a completely beginner-friendly introduction to the field of machine learning. And what we're really going to do is just go over the absolute fundamentals of what the goal of machine learning is, what data is, and how to use it to solve problems. Oh man, I skipped ahead a few here, didn't I? There we go. What data is and how to use it to solve problems. And then we're going to go over a couple of techniques in the different sort of branches of machine learning. And then we're going to wrap up with a very short one-point discussion about the biggest problem you're going to run into when you start trying to apply machine learning to whatever your problem is. So let's go ahead and get started. First things first, we do this in every introductory one. What is machine learning? All right, so I used to work with a guy named Dave Robinson from about 2015 to 2018. Really smart guy, really enjoyed working with him. And near the end of that time, I guess around January 2018, he wrote a blog post called "What is the difference between data science, machine learning, and artificial intelligence?" Okay, and in this blog post, it's a short blog post. Highly recommend you go read it. He basically broke it down to three really quick points, which is data science produces insights, machine learning produces predictions, and artificial intelligence produces actions. Okay. And I really sort of like these, but let's sort of dig in a little bit and see if we can understand more about what this actually means. All right, so first off, data science produces insights. Here you could really replace the word insights with like knowledge or understanding if it's easier for you to wrap your head around. But basically, data science produces facts that are useful in making decisions. Okay, that's the whole point of data science, is to help you decide what to do next. All right. This could be something like identifying that a particular variable in your data has a uniform distribution, which would help you decide which modeling technique to use when building a predictor. Or it could be something like 80% of our customers spend between, say, $1,300 and $1,700 a year with us, which helps you decide what your target should be when you're coming up with financial forecasts or something like that. And then if you read the post, he points out one particular kind of insight, which is causal relationships. All right, and this is something like figuring out what are the most important factors that cause people to stop using your products, right? Which then helps you decide which features you want to add or like improve upon to keep people from dropping off. And I'm calling this one out in particular because causal relationships turn out to be the fundamental basis of predictive models, and machine learning produces predictions. Right? Since machine learning is the point of this talk, we're going to dig into this more in a few minutes. But for now, I just want to say a prediction is really just a guess. You're basically saying, what is the answer going to be? And then it doesn't really matter whether you're right or wrong most of the time. You have to make a prediction. And predictions really only come in two different flavors. The first one is classifications, which is like, selecting amongst a set of options. And then the other one is values. And this would be like, a numerical value of something. For instance, if we were, if I was going to list my house on the market, I want to know, like, what can I sell it for? That's a value. It's a dollar amount, right? But if I was like, what is someone's favorite color? And I want to predict that, well, there's like a finite set of colors for me to choose from. So I just have to figure out how to choose one of them. But they don't have like a numerical relationship to one another. They're just individual and on their own. Okay. So regardless of whether you make a prediction that is a classification or a value, how you use those predictions is the realm of artificial intelligence, because artificial intelligence produces actions. All right. So you have, like, say, 1,000 different advertisements that you could show to someone, and you need to choose one of them. So what you do is you predict how likely a person, whoever is visiting your website, is to buy the product for each one of the advertisements that you have. Okay. And so you get all of these predictions, and then the way that you use those predictions in order to make a choice, and there's lots of different ways, but that is the actual process of like artificial intelligence. I have decided how I am going to choose which of these things to show you, and showing you something is actually an action. Okay, and that's what AI is all about. And if you want like another example of AI, it's like, for instance, you might be playing a game like chess, and you are in a current state of the game. All of the pieces are set up on the board in exactly one way, and then you have to decide which piece to move, and where to move it, right? And whatever action you end up choosing, that is the action that you take. Okay, so I really like these definitions from Dave because they really give you a clear picture of the goal of each one of the disciplines, right? And I feel like when you're learning something, continuously looking at it from the goal of what you're trying to accomplish is a really positive way to make sure you stay on track with your learning. And for machine learning, again, the goal is to make predictions. So let's talk about how you actually go about making a prediction. All right, so to make a prediction, basically you are going to be given a bunch of information about a sample of whatever your problem is, and then you're going to pass it into this thing called an algorithm, and it's going to spit out a prediction, okay? So for a more concrete example, imagine you are like walking into a doctor's office, okay? When you walk into the doctor's office and you've got some sort of illness, we don't know what it is, they start taking things like your vital signs, right? They start measuring your temperature, your blood pressure. They probably get your weight. Maybe they measure your height. And then also they start asking you a bunch of questions. They're like, are you itchy? Are you sneezing? Are you coughing? Where does it hurt? These sorts of things. And all of these little pieces of information all add together to be what we call effectively a data sample. Okay. It is then the doctor's job to take in all of that information, reflect back on all of their training, all of their schooling, all of their experience, and then predict what illness it is that you have so that they can prescribe you the best therapy to help you recover. Okay. And that's sort of the goal. Like that's what a prediction is. But the doctor was the thing making the prediction. And now we want to sort of come up with a better way of doing it. And so we're going to try to apply machine learning, right? The goal of machine learning, the rawest, lowest level goal of machine learning is entirely to make better predictions than any other method we currently have. And that's it, right? For any given problem, here's the best that we can do, and we want to do better. Right. So right now, doctors are the ones making the predictions. We want to do better than that. Okay. And so just think about how significant of an impact this could have. Right. First off, you get the correct diagnosis, you're going to save lives. That's a big deal. Okay. That's a big issue. Second is you're going to improve quality of life, right? Because you're giving better diagnoses, the patients are recovering faster. And so they don't have to be sick nearly as long, which is also great. And then there's also like financial savings as well. Fewer trips to the doctor's office, shorter stays in the hospital. And so it's like, all of these things sort of add together. Like it's a good idea to try and come up with a better way of doing this, which sort of begs the question, where does the model come from, right? Like if we're going to do something else, right now it's the doctor. How does a machine learn whatever this model is that spits out a prediction? The doctor went to school for like a decade. They've got a bunch of experience, with other patients. how does the machine go to school? And I guess like, even more like, can a machine actually learn? And that turns out to be a really fun question to consider. It also turns out to be a very important philosophical discussion. But this talk is really only like 20 minutes long, 30 minutes long, and we're like 10 minutes in. So we're going to skip that, and we're just going to focus on the first question, which was, where does the model come from? And I'm just going to kind of gloss over this a little bit, but here's what it is, right? So this is the process that we're going to use to learn a model using machine learning. Effectively, we have recorded a bunch of historical episodes of whatever our problem is. So I walked into the doctor's office. I was just one person. Then another person came in, then another person came in, then another person came in, and all of these people kept coming in. And so we recorded a lot of data about people being sick and the symptoms that they had. And then we're going to pass it into this learning algorithm, and it's basically going to spit out a model. Okay. And I know this is like whoosh right over the top of the head. I get it. I'm going to give some concrete examples of these learning algorithms in just a few moments. So just stick with me. Right now, though, you should just sort of understand that there are literally thousands of things that you can plug in here, but it's all the same data. The data doesn't change. There's lots of different ways of learning about that data. Okay. And so sort of with all this in mind, I do want to point out that I feel like Dave was a little bit wrong in his definition. The reason is that we don't actually need a machine to learn this model, right? We have other ways of making predictions. So machine learning isn't only about making predictions. There's lots of ways to make predictions. And in fact, we use human predictions all the time. Here's like a really funny one from XKCD, where you just sort of, spit out the same thing all the time. It's the same prediction. Always, always play rock, that sort of a thing. And then I have this aunt, and like, she wakes up every morning, and if she wakes up and her leg, like her left leg is tingling, she's like swearing up and down, it is going to rain today, and it's like, whether that's accurate or not is sort of beside the point, but like, we have these predictors, and like, that's the best one that she knows. Again, the goal is just to come up with a better way of predicting things. Okay. So I think what it actually should have been was that machine learning produces models, not machine learning produces predictions, right? We can come up with tons and tons and tons of models, and the machine is actually learning the models, but the predictor is still sort of the same. You just run whatever your data is through the model, and it spits out a prediction. All right. Let's have some water. All right. One other point I want to make here is that any good model captures the causal relationship that I was talking about earlier. Okay. And this is causal relationships that are present in the data that went into the learning algorithm. So let's talk about the data a little bit. All right. We've been looking at data that looks sort of like this, and we've been saying that like you have these sort of samples, right? For the doctor's office, it was a list of symptoms and like vital signs and just general attributes about the person, like how tall they are and stuff like that. All these collections of measurements, we just call them features. Okay, so each one of the kinds of measurements that we take is a separate feature. So the height of the person, that's one feature. Then the weight, that's another feature. Then whether they're itchy, that's another feature. Whatever it is. And then there's I just want to sort of give you a couple examples here, so you don't think, okay, it's always like measurements of a numerical value. For a game like chess, what we do is actually track the location of each piece on the board, right? So it would be like, where's the first piece? Where's the number one pawn? Where's the king for white? Where is the queen for black? Whatever that sort of thing is. And each one of those things we consider to be a feature. If you were selling a house, it might be something like, how many bedrooms does it have? How many bathrooms does it have? what's the size of the lot? Those are, again, numerical. But then you would have something like, what school district is it in, right? And that does actually affect the value of the house that you would make a prediction from. And so those are, those are the different kinds of features that you can have. And then what we sometimes are also lucky to get are labels, right? And labels are just the correct answers. Okay, so in the doctor's office, we went through this whole process of diagnosing them. We got them some therapy prescribed. They went through the process of going through the therapy, and they actually recovered. So we know that that was a correct diagnosis. And so we record the label of what the correct illness was. And then in the case of like selling your house, it's all of the different things we knew about your house at the time that we listed it. And then sometime later on, you actually sell your house. And now we have a numerical value for what that house was worth at that time, right? And so that's where these labels come from. They're just the correct answer. That's all it is. And for, depending on whatever your problem is, determines what the label is. And again, these labels really only come in two types. There's values and there are classifications. Okay. For any given row of your features and labels, we just call that a sample, right? So this was the one instance of me walking into the doctor, and this was the actual illness that I had when I got there. I just want to point that out. And now I want to get in and actually talk a little bit about the main branches of machine learning, and then sort of how you know when you're in this branch, like why, I should be looking for techniques that are in this branch versus techniques that are in some other branch, and then give you like one or two examples about each one. And the first one is supervised learning. Supervised learning is only possible when we have the labels for the data. When we know the correct answers, that's what supervised means. It basically means I have the correct answers, and I'm going to use those to sort of tell my algorithm when it's wrong. This is like, I have a son right now who's 6 years old. He's been at home ever since, they shut down the schools. And so I've been teaching him to read. And when I'm teaching him to read, it sort of goes like this. He starts reading, and most of the words he just like knows because they're like sight words, but occasionally he will run into a word and he doesn't know it. And I'm like, okay, man, you just got to sound it out. And then he'll sound it out. And we have this rule where as long as he sounds it out and doesn't just, whine away into the middle of the day, if he sounds it out, if he's wrong, I will immediately tell him the correct way to sound it out, right? That's what supervised learning is. You sit there and you like make predictions. And when you're wrong, you are told you are wrong immediately. And not only are you told you're wrong, you are told the correct answer, so that you can adjust as quickly, as your algorithm allows for. In supervised learning is my absolute most favorite machine learning algorithm because it just turns out to be wildly useful for just about everything. It's called logistic regression. Logistic regression basically says I've got these two features, weight and height, and this is just one example. You could have it be whatever your problem was. This was, so this is the doctor's office, for instance, or if you wanted to be like selling your house, it would be like the square footage and I don't know, the average, whether it's in a flood zone, something like that, whatever. And the idea is that we're doing a classification. We're either saying you are, in this category or not in this category. And for this one, it's saying based on the weight and the height, predict whether or not it's a male or a female. And if you were to actually like look at the blues, they sort of come down here. They don't go all the way down as low as the pink dots do. They sort of go like this. And so you can see there's a fair amount of overlap. And what we're going to do is we're going to just draw a straight line somewhere through this graph. And wherever we draw that line, we're going to say that everything on top of it is a male and everything below it is a female. And you can see it's not 100%. It's not going to be 100% accurate. And the goal is not to be 100% accurate. The goal is to be more accurate than whatever other method we have of making this prediction, right? So 100% accuracy, definitely not the goal. But it turns out that this is incredibly useful. These sorts of classifications happen all the time. On a website, you're trying to predict whether or not, a person will click on an ad. That's a yes or no question. Anytime you have a yes or no question, logistic regression is just a really great choice, as long as you have some labels that tell you whether or not you were correct. Without these labels, you cannot do logistic regression. Okay, the next one. So if we have supervised learning, we should have another kind of learning called unsupervised learning. And unsupervised learning is a lot like supervised learning, but you're not allowed to get any labels. You don't get those in your data. They just don't exist, right? And this is sort of the key point that we're sort of getting to here, which is based on the shape of your data, what information you actually have is going to sort of determine what path you're going to take when you're choosing a learning algorithm. So supervised learning, there are just tons and tons and tons of algorithms for supervised learning. For unsupervised learning, it's sort of different. Most of the learning that you do is what's called clustering, okay? Because we don't actually know the labels, we're basically looking at different samples and trying to figure out which ones belong together and which ones don't, okay? For an example here, we have this really famous algorithm called k-means clustering. This is what your data looks like when you get it, right? There's no labels. We don't know the correct answers. And what we're going to do is try and guess which data is related to one another. And in order to do that, we basically say, I think there are 4 distinct values that are important here. And so we just randomly choose 4 points, and then we start running this algorithm over and over and over, and it sort of moves the points around, moves them around, moves them around, and eventually they sort of stop moving, okay? And when they stop moving, we say whatever point the sample is closest to, that's which cluster it belongs to. And now all of a sudden, from having no labels whatsoever, we now have some useful information that we can use for something else, right? And this is a very, very, very wonderful tool. This comes up all the time. K-means clustering is not the only type of clustering, but pretty much all unsupervised learning ends up doing some kind of clustering. More water. All right. Let's see. So that's unsupervised learning. It's the same thing as supervised learning, but you don't have any answers at all. Next, we have what's called semi-supervised learning. And this one is super interesting as well. In this case, we have some of the answers, but we don't have all the answers. And it turns out this sort of thing happens all the time, right? We listed a house for sale and it didn't sell. So we don't actually have the answer. Or the person went into the doctor, they were prescribed something, but they never came back. So we can't verify that that was the correct answer. There's just lots and lots and lots of different ways that you end up in this world where only some of your data is labeled and some of it is not labeled. And it turns out that most of the time when you're in this semi-supervised learning scenario, you have very, very, very few labels, right? Like maybe somewhere between like 1 and 10% of your data is labeled. And that's like if you're lucky. Sometimes it's even as low as like 0.1%. It's just a very small amount, but it turns out that using the few labels that you have, you can actually come up with some really interesting ways of solving problems. And this one is straight from Wikipedia, but imagine, if you're ignoring all of this down here, you have these 2 labels that clearly mark it as, one was had the illness, the other one was did not have the illness, right? And it seems like, hey, if we just draw a line right here, we perfectly separate these two cases, right? But if we graph all of the other data, even the ones we don't have labels for, and we see that they sort of cluster kind of well, right? There's these 2 really interesting clusters. And so now this vertical line separator would incorrectly label a large number of them, right? Instead, what we'll do is we will just predict that these all have the same label and all these have the same label and just sort of fill in the blanks. And once we fill in the blanks, we're right back in the world of supervised learning, and you can go and use whatever algorithm it is that you want to use over there. Okay. That's a fun one. And then the last one, the last like major branch here, is something that we call reinforcement learning. The difference in reinforcement learning is that the samples are actually tied to one another in a sequence. Okay. Um, Reinforcement learning is all about looking at things that happen uh, in stride, in effect, and then making decisions and updating the past, right? So when I see this sample, I might actually update some information about this one and this one and this one, 1, 2, 3, and just sort of go back because they're all sort of tied together, right? They're not independent from one another. And then the like most entry level, or maybe the second most entry level algorithm that we have here is what we call policy iteration. Policy iteration is really like, I have this policy, which basically says, given whatever state I'm in, it is producing a prediction that tells you exactly what action to take, right? And so you have a policy, then you evaluate the policy. You basically say, is it all correct? And if the answer is no, well, policy evaluation, there's two ways you can do it. The first one is, are they all correct? If the answer is no, then you keep going. And then the second one is to basically check whether or not it is different from the previous policy, right? So the first time through, you're not really, you're going to skip this step. Then you're going to do this thing where you learn the new values basically by following the policy over and over. And then you're going to use the values that came out of that to improve your policy if you can. And then you're going to check whether or not they're the same policy. And when they stop changing, then you know you have found the best policy. I mean, it turns out that this is what we call like a type of planning. So if you have a bunch of different actions that you have to take in a sequence, this thing will tell you how to plan for it accordingly. All right. And that covers really the four main branches. There are tons and tons of other little spurs that come off of each of these, but these are the different ways that data is set up. You have supervised learning, unsupervised learning, which has no labels whatsoever. Then you have semi-supervised learning, which only has some of the labels. And then you have reinforcement learning, where each of the samples is actually tied to the other samples. Now I want to get into the absolute biggest problem that you will ever run into with machine learning. And I just don't want you to forget it. It's just one problem, okay? And it's that the most important rule in machine learning is the garbage in, garbage out rule, okay? If you pass in garbage data, it doesn't matter how good your learning algorithm is, you're going to get out garbage predictions. Just completely garbage predictions. This input data is always dirty, always wrong, always has mistakes in it. Sometimes data is just completely missing from your samples, like, oh, we didn't take their temperature when they came in, so we just don't know that. Sometimes you have the situation where you need 2 or 3 features together for it to make sense. And sometimes you're in this situation where there's just not enough features to actually make decisions about. In all of these cases, you have to fix that before you fix anything else. You don't need to worry about this learning algorithm. You don't need to come up with any sort of special anything for it. You just need to fix your inputs, and all of a sudden, it will start producing good outputs. And that's it. That's really it for the talk. Thanks everybody for joining. Since I have about 1 more minute left, I do want to just say, please, please, please donate. I have a friend who was one of my groomsmen about 10 years ago, and I got a call from him about a month ago. And he told me, he's getting married, so I thought he was calling to talk about that and maybe give me some information about it. But it turns out he was actually calling to tell me that both his mom and his dad had gotten COVID-19 and were both hospitalized. His mom recovered almost immediately, but his dad got to the point where he was in ICU. And I got some really good news today. I got a call from him, and he told me that his dad was actually back at home now. So it's just really important to me. I feel very blessed to be a part of this. I'm very happy for my friend and his family. Please, please, please donate whatever it is that you can donate. And again, thank you for joining.